The next topic we are going to see is the increase of entropy principle discussed in section 7-2. So for this we are going to start by considering a cycle between states 1 and 2. 1 to 2 is some arbitrary process. It could be reversible, it could be irreversible, it could be anything. 2 to 1 is an internally reversible process. Okay, we are going to consider this cycle between two states 1 to 2 and then back from 2 to 1 through two processes, one which is arbitrary, no conditions imposed on that, and the other, the return process, being an internally reversible process. For the entire cycle, Clausius inequality may be written as the cyclic integral of delta q over t is less than or equal to 0. And since this cycle consists of two steps, I'm going to split this as 1 to 2 delta q over t plus 2 to 1 delta q over t, but in this case it's an internally reversible process. Internally reversible is less than or equal to 0. The first term is simply 1 to 2 delta q over t, whereas the second term is our definition of entropy that we saw in the last lecture. In fact, entropy definition is written as, I'm going to write this here, delta S, which is S2 minus S1, is written as 1 to 2 delta q over t, internally reversible. By that notation, this would be S1 minus S2 less than or equal to 0. So further continuing, I'm going to write this: S2 minus S1 is more than or equal to delta q over t integrated from 1 to 2, or ds is greater than delta q over t. I want to re-emphasize that temperature in these relations is the thermodynamic temperature at the boundary where heat transfer takes place. Okay, the quantity delta S, which is S2 minus S1, is the entropy change with the process 1 to 2. With the process 1 to 2 doesn't depend on the path, it depends only on the end state. And delta for a reversible process delta S2 minus S1 equals delta q over t from 1 to 2, making this the reversible heat transfer, making delta q the reversible heat transfer. The statement or the equation that says ds is more than or equal to delta q over t tells us that the entropy change in any process is at least equal to or more than that associated with heat transfer. That is, if you write the change in entropy of a system, change in entropy of a system. This is the final entropy minus the initial entropy. This is equal to 1 to 2 delta Q over T plus entropy generated. And since this delta S system is always equal to 1 to 2 or greater than or equal to 1 to 2 delta Q over T, this implies the entropy generation in any process is at least 0 or more than 0. The case when the entropy generation is exactly 0 represents the situation where ds is exactly equal to 1 to 2 delta Q over T, and this process is internally reversible. That is, for a reversible process, the entropy generation is 0, and for an irreversible process, the entropy generation is more than 0. And in general, for any process, the entropy generation is more than or equal to 0, or the change in entropy of a system is either more than or less than or equal to 0. I'm sorry. The change in entropy of the system is equal to the sum of the delta Q over T integrated from 1 to 2 plus entropy generated. Delta Q may be positive or negative. The heat transfer may be, the heat may be added to the system or removed from the system, making this term positive or negative. S gen, on the other hand, is always 0 or positive, which means heat transfer is the only way to decrease the entropy of a system. Without heat transfer, or without considering heat transfer, the entropy of a system always stays the same or increases. This principle or this statement is called the increase of entropy principle. In fact, it can be used to say that if the entropy generation in a particular process is positive, that would be an irreversible process. If it is equal to 0, that would be a reversible process. And if it is less than 0, it's an impossible process, or in other words, the process cannot take place theoretically. So this is usually used, this principle is used to check if a certain process will actually take place. Why do I say that? If I think of a situation like a hot cup of coffee, let's say the coffee is at 120 degrees Fahrenheit, the room is at 70 degrees Fahrenheit. If X joules of energy is lost from the coffee to the room, it is conceivable that we can transfer X joules of energy from the room to the coffee. The X joules is still the same, and we would expect that a coffee that is at the same temperature as the room, 70 degrees Fahrenheit, spontaneously takes up X joules of energy and goes up to 120 degrees Fahrenheit. This we know takes place in reality. This does not take place in reality. The entropy generation in this situation is more than 0, whereas the entropy generation in this situation is less than 0. That is, heat at a higher temperature has the tendency to flow to a lower temperature. Heat at a lower temperature does not have the tendency to flow to a higher temperature, and this process is forbidden in reality. A closing remark about energy and entropy. We saw what was the first law, which says Q minus W equals delta U plus delta KE plus delta PE. This is the first law, which gives a balance of energy in a process or in between the different states of a process. The second law is written in variety of ways. One of them is to write it in terms of the Clausius inequality. The other is also to write it in terms of entropy generated. Okay. What it states is that it tells us the direction of a process. Energetically, a process may be favorable, or energetically a process may be you can do an energy balance and tell how much joules of energy is needed to be transferred between 1 to 2 or 2 to 3 or whatever, whereas the second law tells you whether the process will take place or not. Only processes for which the entropy generation is more than or equal to 0 are possible, and the remaining are impossible processes. And we'll use this principle while solving problems.